Hello everyone, my name is Mark and my call sign is N9WIB. Today we'll be presenting space weather for amateur radio. So space weather, why is this topic important to amateur radio operators or ham radio operators? We'll cover that, and we'll also cover a brief history of space weather and significant space weather events, go into some core concepts and some basic scientific principles about the atmosphere, the sun, and the Earth's magnetic field, and we'll close with solar indices. So how do we measure solar activity? And we'll discover all that stuff towards the end of the lecture. So why is space weather important? So for ham radio operators, this is a very delicate balance. The solar cycle goes in 11-year cycles, at which peak there is significant improvement in radio propagation, meaning that we can contact distant stations in Europe or beyond. And there are also periods where solar activity is at its minimum, meaning that sometimes without specialized equipment or very large or powerful antennas, we really can't talk to that many people that far away. So, but again, there is a balance. So space weather, if the sun becomes too active, then that can result in disruption of radio communications. It can cause radio blackouts, and it can also cause disruption of satellites and navigation. So in the old days, we used to navigate with maps and so forth, but today we become so heavily relied on GPS navigation that a disruption in GPS navigation and satellite activity would potentially be disastrous. And if the space weather or solar activity is significant enough, it can result in transient to serious damage of power grids. So history is a perfect way of delineating exactly how space weather can affect humanity. So there's something called a Carrington event that was a very significant geomagnetic storm that occurred in the first week of September in 1859. So this is 1859. It's not the peak of technology. This is when technology was in its infancy. This was associated with solar cycle 10, and the geomagnetic storm was thought to be associated with what's called a coronal mass ejection, which we will cover in a few more slides. A large solar flare was also observed by British astronomers, Richard Carrington and also Richard Hodgson. The event was so significant that auroras were visible in Florida. So a typical auroral activity or northern lights are visible in the far northern latitudes. I, for one, saw them once in my lifetime, and that was in very northern Minnesota, and they were absolutely incredible. But there was such significant solar activity that caused a disruption in the Earth's geomagnetic field that auroras were actually visible as far south as Florida and possibly even the Caribbean. So at that time of the solar event, during the Carrington event, telegraph systems failed and there were sparks and flames at some station. And today there would be widespread blackouts, damage to power grids, and potentially more and more significant damage. So back then, technology was in its infancy, and today, since we rely on technology so heavily in electronics and our power grids are so complex, a similar event would be potentially devastating. So there is some evidence that other significant solar events occurred in history. There was a recent article in Scientific American in, I believe, December of last year, 2021, that a significant event occurred someplace between 774 and 775 AD. And how do we know this? Well, according to the article, there were increased levels of carbon-14 in ancient trees. This was discovered by a study by Fusa Miyake, a Japanese physicist. And there were also other levels that were elevated in ice cores. So they found increased levels of beryllium-10 and chlorine-36 isotopes were found in ice cores. And these two isotopes, carbon-14, beryllium-10, and chlorine-36, apparently correlate with a significant atmospheric event or ionospheric event with increased solar irradiation or irradiation of the Earth by some type of event. And these increased in isotopes suggest that a cosmic event 10 to 100 times stronger than the Carrington event occurred. And other data suggest that similar events occurred in 7176 and 5259 BC. Of course, back then, we didn't have any advanced technology, but I'm sure there were pretty significant auroral displays. More recently, a geomagnetic storm resulted in blackouts and overloaded power grid in March 1989 in Quebec, Canada. And this resulted in, again, a 12-hour disruption in power to the city in March 1989. And more recently, last year, July 3rd, 2021, an X-class flare, an X-class solar flare is probably one of the highest you can get. There are certain numerical subtypes of S-class flares, the smaller numerical value being weaker and the higher numerical value being the stronger. But in essence, an X-class flare significantly reduced high-frequency propagation of radio waves in North America for about an hour. And some hams just said that the frequency, the HF frequencies essentially went dead for about an hour. I was not operating at that time, so I did not experience it, but it's probably something pretty significant to experience if you're having a QSO or a conversation with someone, and all of a sudden all the frequencies, your waterfall and everything else just goes completely dead and there's no radioactivity. The first thing you'd probably think of is that there's something wrong with the radio, but it was an X-class flare causing disruption in the ionosphere and propagation. And so some estimates suggest that the chance of another Carrington event within the next decade could be as high as 12%. So that's something to be cautious of and watch out for, especially with today's reliance on our technology. So more importantly, how does damage occur? So we know that damage occurs in the telegraph lines and the blackouts on some power grids. But as ham radio operators, as amateur operators, we kind of want to know what the mechanism is and how this actually happened. So from basic sciences and basic principles we've learned in our studies related to ham radio, we know that a time-varying magnetic field can generate current in a wire. So varying polarity associated with time as a function of time in a magnetic field can induce a current in a wire. So it will generate the flow of electricity in a wire. And the opposite holds true as well. A current-carrying wire also produces a magnetic field. So Earth's magnetic field can produce stray current in power lines. And this was discovered by old telegraph operators who noted current flow in equipment when no power was applied. So you can imagine going to operate your telegraph and the thing is supposed to be off, but there is apparently current flowing through the wires from an unknown source. Geomagnetic storms can enhance and change the Earth's magnetic field and overload power lines and transformers by increasing current flow. So the storms will increase the magnetism of the Earth's magnetic field, and then that in turn could induce current flow in our power lines and then potentially lead to overvoltages and disruption of transformers. And the other interesting thing to note is that the frequency of current can also change and be altered by the spikes in magnetic fields. So we know that our household and power grid operate on a 60 hertz frequency. However, if the magnetic fields of the Earth during a geomagnetic storm result in different frequencies, those frequencies can trip or disrupt operation of different electrical devices or cause them to fail. So our next section, we're going to cover some basic science principles. We're going to review the atmosphere according to ham radio and review very basic principles about the Earth's geomagnetic field, and finally review some basic principles about the sun. Our atmosphere, and in the lowest portion of our atmosphere, the troposphere, which we exist, the atmosphere composition of is nitrogen predominantly, it's 78%, oxygen 21%, and argon and other trace gases compose less than 1% of the atmosphere. So again, the very bottom layer of our atmosphere, the portion that's closest to Earth, is called the troposphere. And we're going to take a trip, and the center of our trip is going to be Madison's capital, or Madison's Isthmus. So if we use this as a reference point and start driving west, we could hit the west side of Madison, and that is approximately 6 miles away. And that's essentially the vertical profile or height of the troposphere. It goes from ground level to about 10 kilometers up, or 6 miles. So it's equivalent from driving from the capital of Wisconsin and Madison on the Isthmus to the west side of Madison by the Beltline. And another interesting thing to note about the troposphere is that this is where we live, and this is where the majority of weather occurs. So all the weather activities, storms, storm clouds, rain, precipitation, fog, usually occurs within the troposphere. Sometimes it can kind of poke up into the stratosphere with higher clouds or specific thunderstorms, but the majority of weather activity occurs within the troposphere. The next layer above the troposphere is the stratosphere, and this is between 6 and 30 miles up, or between 10 and 50 kilometers up. So we start off from ground level, go through the troposphere, hit around 6 miles, and then from 6 miles to 30 miles up is the stratosphere. And this is equivalent, for those of you who live in Wisconsin, to driving from the west side of Madison to Mount Horeb. So that seems to be a little bit of a thicker layer, or a layer that's a little bit deeper than the troposphere. And an interesting fact is that 99% of atmospheric gases are in the troposphere and stratosphere. So above this level, there's a paucity of gases and molecules, but they still obviously exist to give us certain types of weather and space weather. But the majority of our atmosphere is within the troposphere and stratosphere. And another interesting note about the stratosphere is that we encounter the stratosphere probably several times a year ourselves if we're active travelers. This is where jets fly. The jets actually fly in the troposphere as well. They have to take off from ground level, and aircraft have to take off from ground level. But this is where cruise level and level flight occurs for the majority of jet aircraft within the stratosphere. And another interesting note is that this is the highest concentration of ozone, or O3. The majority of ultraviolet radiation is absorbed in the stratosphere by ozone. So ozone is a protective mechanism and protects us from excess ultraviolet radiation that is coming from the sun. The ionosphere. So the ionosphere is the next large layer above the troposphere, above the stratosphere, and this goes out into space essentially. The depth of the ionosphere goes from about 50 to 600 kilometers. Those are very kind of approximate values, and there's some overlap in the stratosphere and ionosphere. And in miles, that's about 370 miles up. So you can see that the ionosphere is much thicker than the stratosphere and the troposphere. So some low Earth orbiting satellites called LEO satellites, their orbital path is between 160 and 2,000 kilometers above the Earth's surface. So you can see that some of the LEO satellites are orbiting within the ionosphere. Another name for the ionosphere is, of course, the hemisphere. This is the most important portion of the atmosphere to ham radio operators. This is where all the radio signals either get refracted, reflected, or pass through the atmosphere, or actually get absorbed. So this is the most relevant area for ham radio operators. And if we wanted to take our analogy a little bit further, the ionosphere, if we use Madison as the Madison capital as the central point or the ground level point, it's equivalent to driving from Janesville to St. Louis. And again, that is a much longer ride and a much thicker portion of our atmosphere than the troposphere or the stratosphere. So within the ionosphere, ultraviolet and X-ray radiation from the sun cause ionization of atmospheric gases. The density of the ionosphere depends on the amount of solar radiation reaching the Earth. So the more solar radiation generated by the sun, the more UV and X-ray radiation we have, it will interact with the ionosphere, cause ionization of particles and gases, and increase the density of the ionosphere. And that will directly impact how ham radio or amateur radio waves either are reflected, refracted, or absorbed or pass through the atmosphere. The ionosphere is further divided into D, E, and F layers. The D layer is the closest to our surface. The E layer is next, and then the F layer, or F layers, is the final portion of the ionosphere near space. And again, the ionosphere causes reflection, refraction, and absorbance of radio waves, so it is the most relevant to us. And if we want to discuss more meteorological terms, weather terms, the ionosphere consists of three other layers more related to potential weather-related phenomenon or space weather-related phenomenon: the mesosphere, thermosphere, and the exosphere, going from bottom to top. The D layer exists at around 70 to 90 kilometers, and again, that's equivalent from Janesville to Beloit. So when most of your 80 meter, 75 meter signals are absorbed during the daytime, they're being absorbed in the Janesville to Beloit region with respect to the Madison or state capital. And the D layer is ionized during the day and not at night. So it's mostly ionized during the day, leading to HF radio wave absorbance, and not at night, so the waves are free to propagate further up into the ionosphere. The E layer exists between 90 and 160 kilometers, and that's the vicinity of maybe as far as Elgin, Illinois. I apologize for those of you who are listening in other states that aren't familiar with our geography, but this is mainly targeted for a presentation to ham radio operators in Wisconsin. But you gotta get the gist of the picture. It's ionized during the day and less at night. And then we finally get into the topmost portion of the ionosphere, the F layer, which is at about 160 to 600 kilometers. And this is the thickest portion, the deepest portion. So you're driving now from Elgin to St. Louis. So that's a pretty far trip. So it's a fairly far trip through the atmosphere, especially by car. But you're not going to be driving all the way up there. It's got the greatest degree of ionization and free electrons. Why? Because it's closest to the sun's radiation exposure. So this gets the highest amount of solar radiation. And at night, there are two layers, the F1 and F2 layer, which exist during the day, and those merge into a single F layer at night. And for HF propagation, the F layer usually reflect radio waves up to 35 megahertz, meaning anything above 35 megahertz is going to go out into space. So those 2-meter signals, those 440 signals, the radio waves we produce on FM through commercial broadcasts, those are all going to penetrate through the sequential layers of the Earth's atmosphere, through the ionosphere, and go out into space for others to enjoy in other galaxies and other planets potentially. So, but everything below 35 megahertz is reflected or refracted back down to Earth's surface and has us enjoy the HF radio propagation. This is a great depiction of the vertical profile of the atmosphere. I think I found this on the NOAA website, and it divides things into the lowest layers, the troposphere, the stratosphere, and the ionosphere. And as you can see, the thickest portion of the atmosphere, or the deepest portion of the atmosphere, is the ionosphere. And you can see that it's divided into the lowest layer, D, then E, then F1 and F2 regions at the very top, which again merge into a single F layer during the nighttime. And this is another depiction of our atmosphere with respect to a globe. The D, E, and F regions, as far as their thickness and orientation, are according to the Earth's surface. So what's beyond the ionosphere? What's beyond the ionosphere is the magnetosphere. It's the region of space where the Earth's magnetic field interacts with the solar wind. It's between 600 and 160,000 kilometers deep. So this is far larger than the ionosphere. And if we want to take our car trip analogy, it's like going from the capital in Madison to St. Louis. And from St. Louis, it's 12.5 times Earth's diameter. So you're traveling from St. Louis, and then you're lining up 12.5 Earths, and you're driving that far. So this is by far the largest kind of layer of the Earth's atmosphere, the magnetosphere. And as we'll see in a few more slides, it's not this perfect ball or oval shape that surrounds the planet. It's affected by the solar wind and has a tail and a front-facing portion. Auroral activity, or northern or southern lights, occur between regions of the ionosphere and the magnetosphere. The Earth's magnetosphere protects us from harmful cosmic and solar radiation, so that's another protective layer from the harmful effects of the sun. And this is a depiction of the Earth with its magnetosphere, and from the left you can see the sun-facing portion and the solar wind. So the solar wind is interacting with the magnetosphere and kind of pushing it towards the right portion of the screen, almost like a comet in its tail. So there is some interaction between the solar wind and the magnetosphere to cause physical distortion of the location of the magnetosphere. So in order to have a magnetosphere, we've got to have a magnet, right? So the Earth produces a magnetic field. It extends from the Earth's interior into outer space, and it's actually formed by the movement or convection of molten iron and nickel within Earth's core. And that creates pretty much a huge bar magnet or a dipole. And the magnetic lines of force are nearly horizontal near the Earth's equator, and then they become a little more vertically oriented going into the upper poles and southern poles. And this is a graphical depiction of that. You can see that it looks like the typical dipole orientation of a magnetic field, with the magnetic field lines going into the northern magnetic pole and the southern magnetic pole. And as you can note here, that the northern magnetic pole is not necessarily the geographic northern pole or the southern pole. Those are separated by approximately 11.5 degrees. So the northern magnetic pole is not the geographic North Pole per se. So Santa Claus lives a little further away from the northern magnetic pole. So these are some fun facts about the sun. I came across this while listening to a podcast by Neil deGrasse Tyson, Star Talk, I think. So if I'm mispronouncing that, it might be, it's not Star Trek, it's Star Talk. And these are some interesting fun facts about the sun. So the sun is not a solid surface. It is a large ball of gas. It is 93 million miles from Earth on average, and the distance from the sun to the Earth is equal to 1 AU, or astronomical unit. And what else? It's 12,000 Earth diameters away, so we'd have to line up 12,000 Earths next to each other to actually reach the sun. And another important thing for us is that it takes light that's coming from the sun to reach the Earth. It takes 8 minutes and about 20 seconds to reach the Earth from the sun. And 1 million Earths can fit into the sun's volume. So you can see how much larger the big ball of gas the sun is compared to the Earth. 1 million Earths can fit into the volume of gas that's present within the sun. The sun produces energy via nuclear fusion by the conversion of hydrogen to helium and subsequently energy in the sun's core. So that's how it produces so much energy. The temperature in the visible surface of the sun is between 7,600 degrees Fahrenheit to 10,300 degrees Fahrenheit. So a little bit warmer here than the Caribbean or Florida. And the sun's power output is around 3.86 times 10 to exponential 26 watts, far exceeding the legal limit of ham radio operation. So that's a lot of ham radio operation stations operating at full power. So we're thankful that we're going into another solar cycle. And the sun's activity varies based on an 11-year average cycle, meaning that there's periods of intense activity and then periods of minimal activity. And that activity varies on an approximate 11-year cycle. The solar minimums, meaning that the minimal activity, the sun produces minimal activity, usually last around 3 years. But it could be as short as 1.5 or as long as 8 years. So we could be facing poor amateur radio operating conditions for only 1.5 years or as long as 8 years, depending on the solar cycle. And currently we're in the beginning of solar cycle 25. So we're slowly climbing up that curve, and we'll soon be able to enjoy much better ham radio propagation over the next few years. And this is another graph of the international sunspot number. And the sunspot number highly correlates, is tied to solar activity. So the greater the sunspot number, the greater the activity or solar radiation that we receive from the sun, and the greater ionization we have in our atmosphere. And this is from the 1960s to 2020. And we can see since the 1980s to 90s, we've seen kind of a decreased peak of subsequent solar cycles. So we'll see what this current solar cycle has in store. So hopefully it'll be better than the rest. So the sun produces energy. And what type of energy does the sun produce? Well, it produces energy in the range of visible light, as we know. We just have to kind of look outside and to appreciate that. It produces energy with heat and infrared light. It also produces radio waves. And more importantly, it also produces higher energy waves such as X-ray, extreme ultraviolet, and gamma ray radiation. The actual wave portion, the electromagnetic radiation, takes less than 9 minutes to reach the Earth. But there's something also called the solar wind, which is not electromagnetic radiation per se, but it's full of charged particles. And the solar wind takes about 20 to 40 hours to reach the Earth. So significantly slower compared to the light or electromagnetic energy that's released from the sun. The solar wind is composed again of protons, electrons in plasma form, and it also contains the sun's magnetic field. So it's not just one component, it's a bunch of ionized particles, protons, electrons, plasma, and magnetic field components from the sun. The solar wind varies in speed. Typically, it runs around 400 kilometers per second, and that's a little bit difficult to put into terms. But if we imagine traveling from Madison, Wisconsin to Champaign-Urbana in the central Illinois, that is approximately 400 kilometers. and that would take about 1 second if the solar wind was traveling from the capital of Wisconsin to Champaign-Urbana, Illinois. The faster the solar wind, the greater the effects to Earth's geomagnetic field and ionosphere. So if it's traveling at its typical speed, 400 kilometers per second, it obviously affects the magnetosphere and subsequently the ionosphere. But as the speed potentially picks up, if there's a solar storm, that can cause greater geomagnetic field and ionospheric disruptions, leading to geomagnetic storms and increased auroral activity. Coronal holes are weak areas in the sun's outer layer, and these coronal holes allow a high-speed stream of charged particles to escape from the sun, and this is called the solar wind. So a very rough analogy could be maybe a balloon filled with air, and if you poke a very small little micro hole in the balloon, that air is escaping in a high velocity stream, and that could be analogous to the coronal hole, the hole in the balloon, and the solar wind, the air that's escaping from the balloon. But that's a very rough analogy. So the sun's not going to deflate, and the sun's not releasing any air. It's releasing the solar wind. The coronal holes appear as dark areas on the sun and with extreme UV and X-ray solar imaging, and coronal holes may persist throughout several 27-day period solar rotations. So it takes 27 days for the sun to rotate on its theoretical axis, and that the coronal holes can persist from one rotation to the other. This is a satellite image of the sun, and I'm not sure if this is X-ray or UV, but it depicts some coronal holes on the sun's surface. Now there are events called coronal mass ejections, or CMEs, and these are large expulsions of ionized particles, gas, and magnetic field from the sun surface, much greater than the solar wind or much greater than solar flares. These coronal mass ejections can eject billions of tons of material out into space, and if the Earth is orbiting the sun, if the Earth has the opportunity to have the sun-facing portion of it, then the Earth can potentially be in the strike zone of a coronal mass ejection. The fastest CME can reach Earth in 15 to 18 hours. Again, this is much slower than the speed of light and the wave particles. And satellites may provide maybe 15 to 20 minutes of advanced warning of a coronal mass ejection. And these coronal mass ejections can result in a geomagnetic storm. So again, it's important to remember that if the coronal mass ejection occurs and it's not on the Earth-facing portion of the sun, then it's not going to be within the Earth strike zone. It's going to go out into space and hit something else. And if it's facing Earth or happens to be within Earth's path, then that could potentially be a significant event. Coronal mass ejections result in radiation storms, and protons from CMEs may reach Earth slower than the speed of light but faster than other particles. And protons interact with the Earth's magnetic field and are funneled towards the poles. So the Earth's magnetic field will interact with these protons and then funnel them towards north and south poles. It can cause damage to electronic equipment in space and DNA. So people who are flying at high altitudes in aircraft, or obviously satellites or astronauts on space stations or spacecraft, are going to be at significant risk if there's a coronal mass ejection and that occurs within Earth's strike zone. The CMEs cause ionization in the atmosphere, releasing free electrons in the ionosphere and potentially disrupting HF radio communications. So sunspots. There are areas on the sun's surface that appear dark, and I remember as a kid, I know you're always taught not to look directly at the sun or don't point your telescope directly at the sun, but I think I picked up a solar filter for the telescope at a garage sale, and I actually had the opportunity to put that solar filter in the very weak telescope that I had and see the sun. I'm not sure if I saw any sunspots or not, but that was kind of a neat thing to do. The sunspots are cooler areas surrounding cooler areas and surrounding areas, and have increased magnetic activity. So the sunspots have increased areas of magnetism, and the more sunspots there are, the more solar activity. And the sunspot number is not just a plain old count of how many spots you see on the sun. It's a little more complicated than that. It's other factors that are taken into consideration are the actual number of sunspots, the grouping pattern, and also the size of the sunspots to come up with a sunspot number. And again, this is another depiction of the sun, picture of the sun with magnified views of sunspots. Solar flares are also solar events. They are large eruptions of electromagnetic radiation from the sun's surface, lasting minutes to hours. So this is not the solar wind. This is not a coronal mass ejection. These are flares of electromagnetic radiation that occurs on the sun's surface. And there are varying degrees of flares from smaller to larger. And again, the solar flares travel at the speed of light, so much faster than the solar wind. The increased extreme ultraviolet and X-ray radiation on the sunlit side of Earth results in increased atmospheric ionization. So when this hits the Earth in less than 9 minutes, that increased electromagnetic radiation, extreme UV, and X-rays will cause more ionization within the Earth's atmosphere. The D layer of the ionosphere becomes more dense and absorbs HF radio waves, and causing disruptions in HF communication, specifically on like 160 to 80 and potentially other bands depending on how intense the solar flare is. But this again primarily affects the 3 to 30 megahertz region. Solar flares are classified in intensity based on the peak emissions observed by satellites in the 0.1 to 0.8 nanometer spectral range, again monitored by satellites. So the class of flares, you can have class A, B, C flares, which are relatively minor. The ones that are most important to us are class M and X level flares. And class M and X level flares are also further subdivided numerically. So a M1 flare can cause a minor radio blackout. An M5 flare can cause a moderate radio blackout. Once you get into the X region, so the X1 can cause a strong radio blackout, X10 severe radio blackout, and X20 can cause extreme radio blackouts throughout the sun-facing surface of the Earth. So what do we use to actually measure solar activity? It's pretty difficult to directly measure on Earth because, again, the X-rays, the extreme UV is for the most part absorbed by our atmosphere. We can rely on satellite data, which is extremely useful, and we can also rely on other indirect measurements for measuring solar activity. One of those is the sunspot number, and as I mentioned before, the sunspot number is very roughly a count of the number and type of sunspots on the sun's surface. The international sunspot number correlates with the 11 years solar activity, so the 11-year cycle. So the more sunspots, we know that it correlates exactly with the activity of the sun on an 11-year basis. The average of direct solar observations at several locations. So the sunspot number is not just monitored at one location. It is monitored throughout the entire world, and those numbers are averages and reported. And again, the sunspots, it's not just a simple count. It's the number of sunspots, it's the size, it's the grouping, and then there's a scaling factor that accounts for the method of observation. Are we seeing this through simple telescopes? Are we seeing this through satellites? Are we seeing this through binoculars? What are we doing? So there's a scaling factor for the type of observation that people see. And this is another graph with the solar cycle sunspot number progression from the 1700s through the 2000s. And we can see that this correlates, the sunspot number correlates very tightly with solar. And there's something else that we can use to monitor the solar activity. It's the solar radio flux at 10.7 centimeters. So radio signals are actually generated on the sun, and specifically in the 2800 megahertz range or 2.8 gigahertz range in the solar atmosphere. And that's directly observable on the Earth's surface. So just like listening to radio signals from other ham radio operators or CW or something else, this is a radio signal generated by the sun that is not affected by weather, and there's a very high correlation between sunspot number and extreme UV values. So the solar flux actually correlates really well with other methods of detecting or measuring solar activity. The solar radio flux is measured in solar flux units, or SFUs. It's been measured in Canada since 1947, and the SFUs can vary between maybe below 50 to over 300 SFUs, depending on the activity of the sun. And this is a graphical depiction of solar flux over time, from the early 1900s to the current date. And these, again, positively correlate with the solar cycle, 11-year solar cycle. So we can also measure other things such as the magnetic field of the Earth. And this is typically, there are other methods, but the planetary K-index is the most popular and the most heard of. There are other indices which we won't get in today, but the planetary K-index quantifies the disturbances in Earth's magnetic field. So it essentially measures Earth's magnetic field. The data are obtained from instruments called magnetometers, and magnetometers measure the Earth's magnetic field or magnetic fields in general, and the data is updated every 3 hours. And the planetary K-index goes from a lower number of 0 to a range of 9. And geomagnetic storm warnings are typically issued when the predicted value or the observed value goes above 4. So that indicates a potentially significant geomagnetic event. We also have the luxury nowadays of satellite monitoring, so we don't have to rely on Earth-based methods to observe space weather. There are many satellites out there. The GOES satellite system. GOES stands for Geostationary Operational Environmental Satellites. And the instruments such as the Solar Ultraviolet Imager, or SUV, on one of the GOES-R satellites looks and produces an image in UV format of the entire solar disk. Other things that these satellites can measure are extreme UV and X-rays, and that is in the form of the EXIS, or Extreme UV and X-ray Irradiance Sensor, on the satellite. And then there is also the Space Environment In Situ Suite, or SEIS, I believe. I'm not sure I'm pronouncing that correctly. So this kind of suite of instruments measures proton, electron, and heavy ion fluxes or changes in the Earth's and near the Earth space environment, depending on the orbital the orbit of the satellite. And of course, magnetometers are used by satellites to measure the Earth's magnetic field strength. And NOAA actually has a great space weather site, and it has 24-hour observed and predicted values on their site. It's the Space Weather Conditions site, so it's depicted in color format R, S, and G. And the first one, R, stands for radio blackouts. The second one stands for solar radiation storm impacts, and G stands for geomagnetic storm impacts. And they can vary from 1 to, or a green level, or 0 at a green level, minor, up to an extreme level of 5. So if you look at this website, you'll see 6, either observed values and predicted values in color-coded format, the RSG, or radio blackout, solar radiation storm impacts, and geomagnetic storm impact on the website, and that's pretty good just for glancing at a reference. Ham radio personnel or amateur radio operators are also involved in space weather through HAMSci, and this is a personal space weather station, and this is a citizen science network of monitors that also compose magnetometers that regular ham radio operators can purchase and use to monitor Earth's magnetic field and form a very powerful network throughout the country or throughout the world in identifying what the current values are of the Earth's magnetic field and space weather. And this has been developed at the University of Scranton, Dr. Nathaniel A. Frizzell, W2NAF. And I believe they have a yearly event, HAMSci, which is a series of conferences. I think it's going on around this time of year. I haven't kept up on it, but it's a great resource. I think one year I listened to a few lectures and they were really informative and interesting. Other resources we can look to are the Space Weather Prediction Center for NOAA. So just Google that, and that's where I was referencing those daily prediction values. So the Space Weather Prediction Center through NOAA, and also spaceweather.com. And of course, Dr. Tamitha Skov, the space weatherwoman. If you ever listen to podcasts, she is on various podcasts, and she does an excellent job of giving updated reports on space weather. And she actually has her own website and Twitter feed, and I believe podcast series, and it's very informative and great information to have. So in summary, powerful solar events have disrupted life on Earth in the past when technology was in its infancy. A similar event today with our far advances in technology can cause serious and widespread disruptions of modern life. Electromagnetic radiation and charged particles emanate from the sun and interact with Earth's magnetic field and ionosphere. And again, for hams, there's that very delicate balance between enjoyment of increased radio wave propagation thanks to increased solar activity to possible disruption of communications throughout the world if the sun gets a little too overly friendly or overly active. And for monitoring, there are many ways of monitoring solar activity. Direct observation of the sun through existing satellites that look at extreme UV values, extreme ultraviolet, X-ray, and ionized particle measurements, to orbiting and earthbound methods of measuring the geomagnetic field. And of course, the old reliable methods of looking at the sunspot number and solar flux measurements at 10.7 centimeters. And that's it. We hope you enjoyed the lecture. That's it, 73.